Okay, so I've got an example here I'm going to go through for you. This is about, we're going to add a synchronous motor to an existing facility in order to accomplish two tasks. The synchronous motor is going to drive a mechanical load, so it's going to operate a piece of equipment of some kind, and it's also going to be used in order to increase the overall power factor of the facility. Okay, so what I've drawn out here is what's the information that's given in the question. We have a 850 kVA incoming apparent power. It's operating, this 850 kVA is at a power factor of 0.82 lagging, right? Which means that currently this facility is consuming 697 kilowatts of true power, right? Our 850 times 0.82 gives us 697 kilowatts. Okay, so this is what we already have operating. Now, we need to add on 100 horsepower of mechanical load, so 100 times 746 is 74.6 kilowatts, right? 746 times 100 is 74,600, which is 74.6 kilowatts. And our target power factor is going to be, whoops, 0.95. A 0.95 lagging power factor is still perfectly fine. They're not going to be penalized for that. Okay, so the first thing we have to do is we're going to determine how many kilovars this facility is consuming right now. So we're going to take our 850 squared minus 697 squared. So currently we have 486.5 kilovars of reactive power being consumed by this facility. Okay, that's what we're that's what the facility right now is buying or paying a penalty on, because they're having to get that reactive current from the utility company. We want to be, we're only allowed to have a line current of, we're going to add our kilowatts together, divide by our power factor. So 697 plus 74.6 is 771.6 divided by 0.95. We're allowed, or we're looking to operate at an incoming power kilowatt, or an incoming kVA of 812.2. Okay, which means we're still, because we're still lagging, we're still going to have to get some VARs. We're still going to get some VARs from the utility, right? But as long as that ratio is better than 0.9, facilities aren't going to pay a penalty for that. So a target power factor of 0.95 is good. So we're going to take that squared minus, I didn't add those together. I didn't write it down. Sorry. Our total kilowatts, I should have wrote this down at first. That's what our new total kilowatts is going to be, 771.6. So 812.2 squared minus 771.6 squared equals, take the square root of that. So we're still going to be allowed to get 253.6 kilovars from the utility. The system needs 486.5 kilovars to operate all of the equipment that is still operating there. All the other motors and everything that are running here still require 486.5 kilovars. So the difference between the two of these numbers, the 486.5 and the 253.6, is going to have to come from the synchronous motor. So we'll take the 486.5, subtract 253.6, $232.9 kVARs are going to have to come from that synchronous motor, so that the kVAR, the reactive power, the reactive current needs of all the other equipment can still be met, and we're only going to get 253.6 of them from the utility. Means we have to find a way to supply this other 232.9, which is going to come from that synchronous motor. And our synchronous motor, we know, is going to drive 74.6 kilowatts of load. So we can take that number squared plus 74.6 squared equals, take the, oh crap, so that new synchronous motor has to have a minimum kVA rating of 244.6. Okay, and this is why synchronous motors are, they will often have both a horsepower rating as well as a kVA rating, right? There's a, they can have both. They will always have a kVA rating because there is a maximum amount of current that the windings on that synchronous motor can handle. So we're probably going to buy a 250 kVA synchronous motor, maybe even bigger, and then we're going to adjust our field current so that when it's under load, it's producing the 232.9 VARs or kilovars that's needed to bring our power factor down to 0.95.